Our first speaker is Mr. VAHID KARIMIPOUR, and he will be presenting quantum simulation of physical systems. Thank you.
I'm very glad and honored, in fact, to be here. And I thank the authorities of the EMU University and the organizers, Izzet and Habib, and all other people who I do not know personally yet. I'm very happy to be here to make new friends. I also congratulate you for this organization and for having the good wish and the goodwill to bring peace in the region, because in the previous one we invited somebody from Israel, this time we are inviting somebody from Iran, perhaps next time we invite somebody from Saudi Arabia, and then together we will have more opportunities to discuss science without borders. In fact, I have been organizing a biannual conference in Iran, in Tehran, on the field of quantum information, and our motto is science without borders, because we have to transcend all these artificial barriers which are made by politics for us. Today I want to talk about quantum simulation, and I have to find
escape first.
Escape. And then
Just control.
Control and okay. And the talk will be, according to the spirit of this activity, will be a completely general one without as much as possible technicalities. So I only present the main ideas. So let's start with this first slide, which, as you see, we have seen great transitions in science from time to time, or the way that we do science. Let's see how. Probably most of you remember the old days that we did geometry. It needed a lot of creativity, so you saw that you couldn't solve a complicated problem on geometry, and then your teacher came and drew a specific line. Miraculously, you could solve the problem. So it was very difficult, and it needed a lot of creativity. Then Descartes came, which transformed all this geometry into algebra. So you have to put coordinates on specific points and lines, and then everything becomes algebra, and you can solve geometric problems routinely without that much creativity. It was a very great dip in science. Then, after a century or two, after mechanics, we had to fight with these analytic solutions to solve, for example, a three-body problem. It was very difficult. Still, there is no analytic solution for this problem. And then came numerical solutions with computers. So not only you can solve the three-body problem, you can also solve many-body problems in a very exact manner, and you can predict the behavior of solar system or even much more complicated systems. So by computers, by numerical solutions, we transformed the way that we do science in a very radical way. The same thing happened also in mathematical physics. Then, instead of solving all these differential equations, partial differential equations, instead of having maturity and expertise in special functions, logger functions, Legendre functions, and so on and so forth, then you came up with simulation techniques. So a student, a high school student who is really skillful in making codes, he can do tasks of analyzing physical systems much better than a guy who is who has expertise in mathematical physics, all the mathematical physics. Why we are successful in all this? Let's look at this solar system. We have the solar system and we want to simulate it. We want to predict the future of the solar system. So you have to decide how many variables you have. If we have n, for example, objects, stars and planets, then we have 6 times n variables. You have to store them in some part of the computer, some memory, and then you have to analyze this, to update this data. It's very simple. If n becomes larger, if, for example, you want to simulate a globular cluster or a galaxy, then the number of variables increases. But again, the number of variables is 6 times n. For example, if n goes from 10 to 1,000, the number of variables goes from 60 to 60,000. It doesn't increase in a very bad way. All these problems are categorized in computer science as easy problems. Why easy problems? Because the rate of growth of the memory that you need is polynomial. Instead of, for example, this is the size of the problem, this is this is the size of the problem, and this is the required memory. And it grows as a polynomial, n to the power of k. It's not very bad. In fact, it's not at all bad. All these problems are categorized as easy problems. In fact, if you look at these games of today or these simulations, you can simulate many, many complex, extremely complex phenomena in the screen of your computer, and you can use it for education, for research, for analyzing, and for many, many other things. And there is something deep here, because actually, this is not something like numerical simulations. It's not like something like analyzing differential equations. It's something that it's actually mimicking the real situation in the screen of the computer. So it's actually mimicking the flight, mimicking the landscape, the city, and so on and so forth. I will come back to this point later. So let's see if we can do the same thing with quantum mechanics. Can we simulate a quantum mechanical problem, a quantum mechanical system, very simple system? Consider, for example, the Eisenberg, the spin system with n spins. Each spin has 2 states, and if you have n spins, the number of spins becomes 2 to the power n. So, if you want to solve the Schrödinger equation for this system, you have to store the wave function at one initial moment of the computer and then update it in the same way that we did for the solar system. So you have to store all these amplitudes, the amplitude of all the spins becoming up to the amplitude of all the spins being down, and there are 2 to the power n amplitudes. You have to store it in some part of the computer. How many amplitudes we need? If you have 10 spins, then 2 to the power 10 becomes 1024 bytes. We have something like this. We need something like this to store the data in the computer. What happens if we want to simulate a larger system? For example, a system of 100 spins. Then 2 to the power 100 will become 10 to the power 24 gigabytes. So it's absolutely impossible to simulate such a very small system, which is not realistic at all, because real systems have billions of spins. It's not possible to simulate this in a classical computer. Absolutely out of question. So this is the lesson that we learned. We cannot simulate quantum systems in classical computers. And this was recognized by Feynman many, many years ago. And he came up also with the idea of the solution. The solution is that we should use a quantum system to simulate another large quantum systems. So use a simple quantum system to simulate another quantum system. This is the idea of quantum simulation. And there are 2 types of quantum simulations. I will describe one at length and then I will say a few words about the other at the end of my talk. So we want to solve this Schrödinger equation. What do we do? If we have a quantum simulator in the future, I'm saying that we are at the edge of a new transition in science, in the sense that quantum simulation will overtake. If quantum simulators are built, then there will be a new transition. If you have a quantum simulator, you can simulate with this large molecules in quantum chemistry, in biology, and so on, the behavior of these things. You can simulate the solids in solidistic physics and so on and so forth. And even you can simulate quantum field theories in the most advanced case. So this is a new transition in science. After the transitions, after the giant leaps that we have made in history. What a quantum simulator is made of? The quantum simulator is made of bits which have been quantized, or qubits. What is a qubit? Any computer that you see stores information in the form of spins or bits, which can be either up or down. They can be either 1 or 0, not both. But a qubit is a quantum mechanical object, which can be 0 and 1 at the same time. It is a superposition property of quantum mechanics. It's a unique property which allows you to do this quantum simulation. So we need qubits which can be prepared in specific states that we like. It's very important. Which can be manipulated. Their state should be changeable by means that you dictate, and they can be measured. Note that we are now talking about single atoms. We do not want to control billions of atoms. We want to control single atoms. This atom, this atom, this atom. We do not want to put this atom from here to here. We want to go into the inside of the atom and manipulate it. And these possibilities have been made realities in these days due to the advancement of nanotechnology, quantum optics, atomic physics for the past 60 years. So a qubit is a two-level system. It can be an atom, it can be a photon, it can be a quantum dot, it can be a spin, and there are many, many candidates for these qubits. Many universities, institutions, research institutes are working on different candidates of qubits and quantum simulators and quantum computers. The essential thing that you should have control over these two states. This is one of the architectures for qubits. It's a superconducting qubit. A superconducting qubit is nothing but a harmonic oscillator, but since the levels are the same, we want to distort it so that we have control over only two states. And there are many different kinds of it. We have to be able to manipulate it, to change the state of the qubit. So we start with the state 0, and then change it by a unitary operator to this specific state. This is called the quantum gate. And we are able to make many, many quantum gates to manipulate the qubits. And there's also a CNOT gate. CNOT gate is something which is very specific. It acts on two qubits, and if the top qubit is 0, it doesn't do anything. It just acts like a unique operator. If the top qubit is 1, then it negates the below qubit. That's why it's called CNOT gate or controlled NOT gate. So it acts like a NOT, but it's controlled by the qubit on the top line. That's why it's called a CNOT, a control line. This is essential because with just these two kinds of gates, you can make any complicated unitary operator, no matter how many qubits you have. And the totality of this is a quantum circuit. And finally, you have to measure the qubits 1 by 1 or 2 by 1. You have these possibilities. Once you have these three characteristics, you have a quantum simulator. And the essential steps is that you prepare states at some point, Then you make it evolve according to your Hamiltonian, whatever it is, and then at the final stage, you measure whatever you like. You measure the expectation values, the observables, whatever you like, and then you acquire information about the physical system. Now let's go a little bit into this technicality. Suppose that I have 9 spins. I want to evolve these 9 spins according to the specific Hamiltonian. How should I proceed? Because I have to make it as simple as possible. There are links which specify the interactions, and these 3 links do commute with each other because they are acting on different links. These blue lines, I put them aside in one part. Then there are these 3 links. Again, they commute with each other, but they do not commute with the blue ones. They have some contact. Then another 3 links, they do not commute with other links, but they do commute with each other. And finally, the other ones. So I write the Hamiltonian in this form, H1 plus H2 plus H3 plus H4. Each category of links, they commute with each other, but they do not commute with the other parts. And then I use this formula, which is called Trotter-Suzuki formula, and write this in this way. I repeat it many, many times, and then I can evolve the state according to this given Hamiltonian. Something like this. This is the direction of time, and this is the gates that you apply. Note that this is not the hardware of the classical computer. You do not wire anything. It's just the direction of time. This is just the direction of time. So you apply these pulses to your simulator, then these pulses, then these pulses, then they repeat, and it's controlled by a classical computer very rapidly. Let's solve a very simple example. Suppose that you want to solve the Schrödinger equation for a single particle in a box, right? Of course, we can do this with classical computers too, but just as an exercise. We want to simulate, we want to use our quantum simulator to solve the Schrödinger equation for a single particle in a box. This is the Schrödinger equation. And suppose that I have just 1 qubit, because qubits are very expensive. I cannot afford to buy or to prepare 10 qubits, so I have just 1 qubit. As you know, the IBM company has made a huge quantum computer which fills this room, perhaps even more, and has only 20 qubits. So it's very expensive to make quantum computers. I have just 1 qubit, which is this one. Yes, and this is the wave function. Since I have 1 qubit, I can coarse grain and divide the box in 2 halves, the left half and the right half. If the particle is in this left half, I call it 0. If it's in the right half, it's called it 1, the state of the qubit. And this is the wave function which has been coarse grained. Cosine of phi is the total probability of the particle being in this side. And sine squared of phi is the total probability of the particle to be in this side. So it's a very simple simplification of the wave function of the particle. And then I can prepare a gate which start from this state 1, 0 and puts it into this initial state. So by this single gate, I prepare the initial state of the particle. But you can say that it's not a very good approximation. It's not a good approximation at all. You can use then 2 qubits. With 2 qubits, you can divide the box into 4 parts, and then you can encode the different parts of the box by 0, 0, 0, 1, 1, 0, 1, 1. Now you have a better approximation of the wave function because it has 4 amplitudes. And then by a more complicated gate, you can again prepare the state. The state is prepared in this form. And then if you go up and up with 3 qubits, you have 8 partitions, and then with only 20 qubits, you can partition the box into 1 million subpartitions. Then you can simulate and prepare the state with very high accuracy. So, up to now we have solved the dynamics of the quantum system, how to solve the Schrödinger equation. But all of us as physicists are very interested in finding the eigenvalues of a Hamiltonian. We have a Hamiltonian, we want to find the ground state or the excited state. How do we do this? The main idea is still here. By the way, if there is any question, please stop me and then we will discuss. Suppose that I have a very simple Hamiltonian. This is the idea, but it works for larger Hamiltonians too. Suppose that I have a Hamiltonian, H. By H, I can make a unitary operator U, which is called e to the power minus IH. And now I have a gate, which is a controlled gate. Again, these type of gates, this type of symbol stands for the controlled gate. It means that if the top qubit is 0, it doesn't do anything. It acts like identity operator. If the top qubit is 1, then it acts like the U operator. So it is the U operator, but it's controlled by the status of the upper qubit. So I put this kind of gate. What happens if I put 0 plus 1 on the top gate? If you follow the argument and follow that quantum mechanics acts linearly, then the output state is 0 times psi, because in this part, the U operator has an act on psi, plus 1 times U over psi, because in this part, the top qubit has been 1, and then you have to act by U on psi. So this is the superposition that we have on these two qubits. Now what happens? Because we want to find the eigenvalues and the eigenvectors of H. So I feed an arbitrary state here, A E0 plus B E1. E0 and E1 are the eigenstates of U. We do not know these E0 and E1 beforehand because they are the eigenstates which we are in search of themselves. We want to find these E0 and E1, but we know that any arbitrary state can be expanded as superposition of E0 and E1. So we put such a state below, and then we expand. And we know that U is acting on this state. So if the first qubit is 0, nothing acts on this state, so you have A E0 plus B E1. But if the upper qubit is 1, then it's acting on this, and e to the power E theta 0 and e to the power E theta 1 are the eigenvalues of this, which we are in search of. We want to find these two eigenvalues, which we know they are pure phases. We're a little playing with these things. If you rearrange this state, you will see that the final output state is this one. I have done nothing here. I've just rearranged the qubits. And this lives on this part and this qubit. This also lives on this part, and E0 and E1 lives on the lower qubit. Again, we cannot do anything like this. We cannot find the eigenvalues of eigenvectors, but we can do a gate, which is called the Fourier transform gate. The Fourier transform gate is done very, very rapidly, extremely rapidly by a quantum computer, and turns this one into theta 0 and turns this one into theta 1. So the final state is something like this. Now a very peculiar property of the wave function is in action. This is the final state. This is the eigenvalue of Hamiltonian theta naught. This is the eigenvector. This is another eigenvalue, and this is the corresponding eigenvector on these two qubits. So if you measure this, and you obtain theta naught, immediately the wave function collapses to this part. So you obtain the eigenvalue from this and eigenvector from this. And you repeat this. You repeat this repeatedly, and then you find the eigenvalues of the Hamiltonian on the upper qubit and the corresponding eigenvector on the lower qubit. And for any Hamiltonian, you can do this, and you can find the spectrum, which is very important in physical sciences. Okay. I'm surrounded by experts in gravity and string theory and particle physics. So I should be very cautious. I say that this is a giant leap for the future, but by future I mean that perhaps 50 years from now, perhaps 100 years from now, nobody knows. But we can extrapolate from the past in the same way that computers, classical computers, have revolutionized sciences in the old way that we knew and we were used to. The quantum simulators can also revolutionize the way that we are doing science in the present day. And the standard model of particle physics is the most basic theory that we have. We know the particles, we know the gauge particles, we know the interactions, the fields, and so on. But calculating with these theories, QCD is extremely difficult, especially if you go to non-perturbable regime. There are many, many things that we do not know because we cannot calculate. Hopefully, quantum simulation can do this. What is the basic idea? The basic idea is, again, dynamics. You prepare the particles. What does, for example, LHC does, or other accelerators? They prepare particles, they shine these particles together, and they come to an interaction, interact with each other. This is the evolution, and then they scatter. And then, at the output, you measure the angles, the momentum, or the identity of the particles. So, essentially, you have a preparation of the states, evolution of the state, and the measurement. And if you are in possession of a large quantum simulator with thousands of qubits, not these qubits that IBM has, this is for the future, then you can store these initial states into the quantum simulator. You have to use, of course, millions of qubits. Then you evolve these qubits according to the interaction of the standard model that we know. And then you measure the outputs, qubits, to answer many, many questions. Which particles have been produced? At what angles have been produced? What are the scattering sections? What are the bounded states? And so on and so forth. Again, I insist that we should extrapolate from the old days to the present day. Nobody in 1900 thought that they could solve all these complicated problems of today by just using a laptop. It was out of question. So what I say is something about the very far future. The theoretical setup has been done, but we are waiting for a quantum simulator to be constructed in experiment. In perturbed regime, all these questions are answered by Feynman diagrams. So you do a lot of calculations by Feynman diagrams, but if you want to make it more precise, you have to use many, many more Feynman diagrams. For example, for a problem like scattering cross-section of Higgs, you have to use many, many Feynman diagrams, and you have to do a lot of calculations. But then, if you have a quantum simulator, maybe you can do this in a very efficient way. All that I said was about which is called digital quantum simulations. By digital quantum simulation, we mean just this. You have a simulator, circuit, a quantum circuit, you prepare the initial state, evolve it, and measure it. But by quantum, by analog quantum simulation, which is the spirit of this picture, you have something, a quantum simulator, which behaves as if it is the system that you are interested in. It behaves as if it's a quantum field theory. So you have a bunch of qubits, an optical lattice, for example, something like this. This is an optical lattice. Nowadays, people are capable of preparing these optical lattices. It's a collection of laser lights coming in different directions and producing standing waves in 3 directions. So it's something like an egg box. You have seen egg boxes every day, and you put, instead of eggs, atoms in these holes, and then you can engineer many types of interactions between these atoms. You can work and you can tune the frequencies of the laser pulses. You can tune the intensity of the laser pulses, so you can change the interactions, the distances, and so on and so forth. So these things we can really mimic many more complicated physical systems. In the same way that in the picture that I showed you, you do not have a pilot or a plane or a landscape in your computer. You just mimic that it is. It behaves as if you have the real thing in your screen. So by this quantum simulator, by this optical lattice which can accommodate thousands of atoms, you can simulate complicated physical systems. This is the picture of one of these optical lattices, and they are really being done in experiments, but not, again, we are not at the edge of simulating particle physics, but the theories have been formulated. And maybe, this is the last slide of my talk, maybe in the future, instead of quantum field theorists, we need people with expertise, which I call it quantum simulationists. This is a new word. Maybe if you are a good quantum simulationist, then you will be paid much, much more than a quantum field theorist, because you have the capabilities to work with these quantum simulators in the future. Some keywords for the literature. The initial person, I think, that who did the real thing was Seth Lloyd. If you want to study more about this simulation of particle physics system and condensed matter system, you can look these 2 names, Ignacio Sirac and Peter Zoller, and many other names of them, but this is a review article in this field. And my own contribution have been in the preparation of states and engineering the states and transfer of states from some part of the lattice to the other part, and so on and so forth. Thank you very much for your attention.
Any questions?
Do you really hope that we will really build a quantum computer someday? I mean, we are making all these simulations, but on the market, those quantum computers which they advertise are not. I mean, they are just ordinary with few additions which do not improve anything at all.
That's right. The quantum computers of today have few qubits, depending on the architecture, because there are many candidates. Some candidates have low equivalence time, some candidates have low gate operation time, some candidates are not scalable, but there are many, many candidates. And the most promising is the superconducting qubits, which can hold thousands of qubits, like the one that they are working on Google or Microsoft. So the answer is just, we have to look at the history. Probably you have heard this story of Faraday. The huge technologies that we have today for all these megawatt power plants started from a very simple experiment, just Faraday putting a magnet inside a coil. That's all. So we are at that stage. We should not be disappointed. We should be hopeful to make such a thing in the future. Yes, please.
Just, I wonder if you in Iran have 1 qubit circuit technically.
Yes.
Do you have some achievement in this area? 1 qubit circuit.
1 qubit.
Of any types.
Yes, in the sense that it depends on which architecture you mean, but suppose that we have, for example, NMI. you have a large molecule of 7, for example, qubit or 5 qubit, or suppose that we have organic molecule, just 1 qubit spin. And then if we want to do some projects with that, we try to construct arbitrary gates on that qubit to rotate it in any direction that we want. Once we do this, of course we cannot publish it because it's trivial. Then we go for the CNOT operation, because CNOT is very important. It's the CNOT operation which allows you to make arbitrary unitary gates on many things. And that's very difficult. So our next stage is that to put another qubit besides that qubit that you said, and then do the CNOT operation. Yes, please.
You have shown an evolution
Yes.
equation in terms of Hamiltonian.
Yes.
Is there any constraint on the Hamiltonian?
No. There is no constraint, actually. By constraint, I do not. Probably you are saying that you're talking about this Dirac constraint or something like
No,
that?
because in the evolution equation,
Yes.
when you initiate the system with an initial condition,
Yes.
there is a term in front of it, e to the something Hamiltonian,
Yes.
and then its future time evolution.
Yes.
If there is no constraint on the Hamiltonian,
Yeah.
how we will know the future time evolution?
We make the Hamiltonian.
Okay.
We have the initial state and let it go. And after a time, we have this future state.
That Hamiltonian is a PROF, the second order differential operator, isn't it?
Anyway,
So it may have an extension.
extension in what sense?
What if it is, for example, positive and symmetric operator,
Yes.
it may have an extension. So we should know which extension is used for the future to predict the evolution.
Oh, okay. I'm not familiar with this idea of extension. I'm just thinking about, for example, spin systems, right? If you have a bunch of spins that have two-body interactions, and then we can evolve this. But maybe we can talk, I learn from you this extension.
I were also similar things,
Yes.
so I try to find establish connection.
Yes, we can talk about this later.
Yes.
I will learn from you. Thank you. Yes, please.
First of all, thank you for the talk. It was very interesting. Second of all, I'm interested to know, for working with 1 qubit that you have the experience, how much time do you need to spend? I mean, how much time it will take?
Again, it depends on the architecture.
Okay.
But the times are of the order of millisecond, nanosecond, and so on.
So that's
So
good.
time is very, very short, extremely short.
Thank you.
In fact, you can subscribe to this website of IBM. They allow you to work with 6 qubits. You write your quantum computer program, you send it to them, and then, of course, you are in a line, and then they send back the answer to you immediately. Yes, please.
Actually, I have 2 questions. First of all, I would like to understand about the optical lattice thing. Optical lattice provides a mean to store some qubits, right?
Yes.
The proposal about optical lattice is that. I guess IBM is not using something like this, right?
No.
They are using some different.
Yes.
And the other thing is, let's say we have some optical lattice, we have some several qubits. Is there a guarantee to have a way of mimicking anything, any kind of interaction, or
It's not guaranteed. It's not a proof that you can engineer any type of interaction. But people have tried to mimic many systems in complex matter systems, and in particle physics, even in gauge theories. Of course, not all gauge theories, but the papers that I told you about, in papers of Zirac and Zoller and so on, they have tried to mimic gauge theories of certain types.
and mimicking about interactions, they are just mimicking the non-linear interaction directly, right? Not a perturbative expansion kind of thing.
No.
Direct
Direct interaction. Yes, please.
I'm just a little bit confused. Like, what is a qubit? Is it a mix of?
Would you please speak louder?
Just a little bit concerned. I'm confused. What is a qubit? Is it a mix of elementary particles, or is it like a quantum particle, or I don't know what is a qubit?
A qubit is just a two-level system. For example, suppose that you have a spin, which can be up or down. This is a qubit, because simultaneously it can be in the state 0 plus 1. Suppose that you have, for example, a hydrogen atom, right? A hydrogen has many layers, many levels, billions of layers. But you can pick up just two levels, and it signifies that the first level to be 0 and the other one to be 1. Because you will be tuning the frequency exactly to be this difference. All the other levels become irrelevant, become dark, and you have just two light, shining states which you can control. That's a qubit. Yes, please, the chairperson should take time.
No, we have still 5
Yes,
minutes.
please.
How do you collapse Schrödinger's equation in those qubits? Because there are many different possibilities, and what do you do in order to collapse the equation? What do you shine in?
The Schrödinger equation, the state collapses automatically, randomly to one of these outcomes. And we use any outcome. We repeat the experiment many times, and we find the statistical data that we need. This is not a substitute theory for the theory of collapse. We are not going behind the standard quantum mechanics. We let the state collapse when we measure it, and since it collapses randomly to different outputs, we use the statistics and we take the average and we find the expectation values of the observables.
Okay, I think if you have extra questions at the break time, you can continue to ask. So now I would like to kindly invite Professor Dr. Ali Aliyev to give his speech.
Thank you.